welcome to the seminar this week, and thank you for coming. Today, our speaker is Professor Mahn-Soo Choi from Korea University in Seoul. So, I will say a few words about him. He got his PhD in 1988 from Postech, also in Korea. And then he spent his postdoc in the University of Basel. He stayed until 2000. After that, he visited many universities, including this one. Okay. And his main research topics are quantum transport, especially in strong correlations like quantum effect. And also he has a strong interest in quantum information. I'm quite happy that he's here. Actually, our collaboration started more than 10 years ago. And I recently checked that together with Rosa and Mahn-Soo, one of our papers, one of our highly cited papers in Google citation. So he will speak today about the quantum capacitor resistor circuit with Majorana Fermions. Thank you.
Well, thank you very much for being here, really. And I have to thank David, Rosa, Florence, and also his director. Thank you very much. Today I talk about some very simple, probably one of the simplest circuit, capacitance resistance RC circuit, but in the quantum limit. David tipped me that most of the students are probably coming from the statistical mechanics groups and probably are not very familiar with these condensed matter systems. So probably I go through many introductory materials, as many as possible. So I apologize to professors. Probably might be boring to professors, but I have to respect the majority of the audience, I think. This work, I did a few works on this in this direction, and for example, in collaboration with Rosa and so on. But I'm not very good at putting several things into a single talk, so I just focus on this single work, and this particular work was done in collaboration with Mr. Lee, who was a former student of mine and now a professor in Seoul. Okay, let me start very slowly. Let's think about the simplest circuit. I have here a resistor. This resistor is my system. It's a small piece of conductor. And if I want to make a measurement of resistance of this conductor, I should put in this between this metal contact, and I should apply a voltage. Then I will have the resistance or the conductance. But as you all know, this the conductance of this conductor depends on length and width and the material property. So usually the ohmic law tells us that this conductance should be proportional to width. Of course, the wider you have a better conductor, and inversely proportional to length. And this is just a material property. And now this is the result, the measurement result, which is done quite long ago now, by now, two groups. And you see, apparently, roughly it is proportional to the gate voltage here. The gate voltage is controlling basically the width. So you can say that gate voltage is proportional to the width. So if the width increases, the conductance roughly increases, but not completely linear way. You have clear staircases here, and the staircases have an even size, and the unit is given by some fixed value. So this is the famous conductance quantization, and you can understand it quite. It's easy to understand this once you introduce the wave nature of a particle. So let's suppose that we have a piece of conductor. It's my system, and you have a finite width, and therefore, according to the quantum mechanics rule, you have a quantization, which is proportional to this, and now you have another quantum number. This governs the quantization in this direction, and in this direction is an infinite system, and you have a continuous dispersion. And here I draw several dispersion relations, and with different quantum number n. So n equals 0, 1, 2. So because this is a fermionic system, you have a finite Fermi energy. So at 0 temperature, up to this level, all energy levels are filled. Because of the Pauli exclusion principle, these electrons well below the Fermi energy does not contribute to the conductance, and only the electrons at the top or at the Fermi energy contribute. But all these contributions are the same because it's a one-dimensional propagation. You have a finite wavelength or momentum, and therefore the contribution is all the same. So that's why in this particular example, you have three units of some conductance. And in this case, the conductance unit is given by the quantum conductance, which is written here. And now, so once you take the wave picture of the particle, then it's pretty easy to understand. Let's move on and take another element to this circuit. So now I have the resistor as before here. So this again, the width of this conductor is controlled by the gate voltage here. And now you have this capacitor. So it's at DC limit, it is completely short. It is broken circuit. So you have a resistor corresponding here, and you have capacitance here. So usually in the macroscopic limit in everyday life, we can see that this circuit is described by the finite frequency impedance, and it consists of real part and imaginary part. Real part comes from this resistance, and imaginary part comes from the capacitor. And so now the question is that if we reduce the size of this system, what would happen? So we could expect some quantum effect, and indeed we have two quantum effects. One comes from the correction to this capacitance, and another the correction to this resistance. So let's first discuss this correction to the capacitance. Capacitance, if you could put many electric charges on a plate, then you have bigger capacitance. But if you decrease the size of this capacitance, you cannot just put in. You have to overcome, of course, the Coulomb recursion, but also you have to overcome the quantization. So if you have a finite system, according to the quantum rule, you have to quantize the levels. And how many quantized levels you have, you can put more electrons for the charged particles. So it all depends on how many levels you have. This is measured the density of state. So you have in addition to this geometric capacitance, you can have a correction due to this finite density of state. So this is quite easy to understand. Now, more difficult part is this resistance, the correction to this resistance. Here recently, in 2006, they measured this resistance in a real experiment by the ENS group, and you see the resistance is finite. It doesn't depend on the material parameter at all. It doesn't depend on how you shrink the resistance and so on. It doesn't depend on the transmittance. It doesn't depend on the gate voltage, and the value is universally 1/2 of the resistance quantum or conductance quantum. So apparently, this imaginary, the real part of the impedance behaves quite strange way in quantum limit. And so how to understand this strange behavior is the essential topic of my talk. So in the usual case, we can understand this quantization of real part in a very simple picture again. Okay, so we have a continuous dispersion relation. Let's take a simplest example. So in general, you could have many quantized dispersion relations, but let's suppose only one band is occupied, and you have this quantum dot, which is connected by this fermionic coupling, which forms the resistance. And now, this resistance is responsible for the dissipation of energy in this system. So we have to figure out how the energy is dissipated in this system. But let's think about the simplest mechanism through which the energy is dissipated in this system. So here, one way is you take out this electron and you have to put somewhere here. And then, of course, the energy is not conserved, and this could be only the virtual process. You can preserve the energy by taking one electron here and the fill off. So the final result would be something like that. So you take out electron, and instead you fill in. Of course, you have this finite difference, and therefore you don't have energy conservation, but this energy can be provided by the AC voltage. So depending on the frequency, you can have this amount of energy shift, and you have created the particle hole excitation. Eventually, this particle hole pair is dissipated in the contact. So this is the main mechanism for the dissipation, energy dissipation in this system, and therefore we have to estimate how many particle hole pairs are created through this mechanism. And you can make an estimate using this simple analysis, just how Fermi would look like estimation, and it involves this. At zero temperature, if you take the derivative of this Fermi distribution function in the delta of P, and delta, and therefore they are completely cancel each other, and you have this universal value. So through this particle hole pair creation mechanism, you can understand it's a universal conductance in this system. So this has been predicted by mathematical quite a long time ago, and only recently was confirmed experimentally. And now, so instead of these usual Fermi channels or usual conductor, I would replace the system by the Majorana epsilons. So for example, 2 Majorana states, and the rest is the same. So the system is still the same, resistance and capacitance, but this resistance consists of, resistor consists of, instead of usual fermions, it consists of Majorana fermions. So of course the question is, why would I think about the Majorana? So it is because Majorana has a quite unique, quite interesting property, and here I want to properties of Majorana fermions. Majorana fermions, of course, it is in English, plain English, it is called fermion, which is its own antiparticle. So here the fermion is important. For example, if your neutral boson, like a proton, So it's neutral bosons are all their own antiparticle because they don't have charge. But a photon is one of the typical example, and you also have this pion, neutral pion. There are three kinds of pions, but if you take the neutral pion, they are their own antiparticle. Radon has not been observed yet, but if they exist, they is expected to be, again, they are antiparticle. So because the neutral bosons are trivially their own antiparticle, they are just boring. But for the fermion case, it's not so trivial. So let's suppose think about the simplest fermion, the spin 1/2 particle. It is described by this famous Dirac equation, and at the time, but they are matrices, and they have to satisfy these anti-commutation relations. At the time of Dirac, the algebra of these coefficients were not known well, but these smart Dirac and actually, if you find the usual representation of these matrices, then usually they are complex, meaning that the solution psi should also complex. If they are complex, they should be charged, and therefore there cannot be antiparticle themselves. So this is a usual Dirac fermion. But in 1937, Majorana found pure imaginary representation of these matrices, because these are pure imaginary, which I demonstrated here. Sigmas are typical 2x2 Pauli matrices, and then you can see that the solution of this equation could be real, at least mathematically. So if the solution is real, then this psi describes a neutral fermion, and therefore it should be an Majorana fermion, or antiparticle itself. And Majorana suggested that probably the neutrino might have this character, and probably the neutrino would be the Majorana fermion. And interestingly, this Majorana was a very, very mysterious person, and even after finding this result, he didn't want to publish it, and his mentor and supervisor, Fermi, persuaded him finally, and he allowed Fermi to publish his paper by his name. So that's how we got to know this Majorana fermion. Anyway, so if this is true, then we could have quite interesting property that it should be its own antiparticle, and then because this is a real, all real variables can be made of one complex variable, or if you have two real variables, you can construct a single complex variable. In the same way, if you have two Majorana fermions, then you can construct a single Dirac fermion. And therefore, Dirac fermion, of course, satisfy the usual anti-commutation relations. And if you try to create or annihilate Dirac fermion twice, then it is impossible. And that is the principle behind the Pauli exclusion principle. But if you, as you see here, Majorana fermions is antiparticle of itself. Further, it has this anti-commutation relation, which tells you that even if you try to create two Majorana fermions, you still have finite probability, finite amplitude. So this particular property I'm trying to exploit in my work. In other words, let's think about the collision experiment. let's suppose you have a particle and antiparticle. If you collide them, then you annihilate them. And as a result, a photon is created. And now suppose that is because of this commutation relation, this relation. But let's try to take two Majorana fermions. You collide them. And this tells us we don't have to annihilate them. And so you can think of these two collision experiments. If you collide Dirac fermion, anti-Dirac fermion, electron, positron, they annihilate themselves and it produces photon. But if you collide Majorana and Majorana, you can have Dirac and anti-Dirac at the same time. So the result is a linear superposition of this anti-Dirac and anti-Dirac. So instead of photons, you can have particles. You collide Majorana, and then as a result, you could have matter or antimatter. So in condensed matter physics, this particle corresponds usually to electron, and anti-particle usually corresponds to hole, positive charge. So this particular property has been already investigated in several hypothetical experiments. Unfortunately, it has not been realized in real experiments. So, for example, the Spinakers group and Fu and Kane group proposed such an experiment where I will not go to the details. So here, if you just accept me, then here you have a Majorana modes and here Majorana modes. And Dirac comes in and it splits into two Majoranas and they collide them again and produces Dirac or anti-Dirac here, electron or hole. So here also, we could consider some slightly different experimental setup. The Dirac or electron comes in and it splits into two Majoranas. Another electron comes in from different port and they split two. And these two Majoranas collide with each other and produces electron or hole. So now, if you have such a scattering, then you can have either electron minus charge or hole plus charge. And it's a huge fluctuation of charge. So this will create, if you collide Majorana fermions, you will introduce lots of fluctuations in the charge. So that's the main idea behind these works. And now here in this RC circuit business, I also exploit this thing. So again, my system consists of these Majorana fermions coupled to quantum dot. The simple version is the single level, and these tunneling couplings forms the resistance, and here you have capacitance. So I think I have explained enough motivation why I consider these Majorana fermions. So here the main purpose is to identify the role of the Majorana fermions played in this charge relaxation or energy dissipation mechanism. And therefore, I want to separate one Majorana, because if the Majorana fermions they appear in the same space, it's just mathematical. You can always decompose Dirac fermion into two Majorana fermions, but they are just mathematical. There's no physical consequence. But if you split them separately, spatially, that is a completely different story. So therefore, here I want to continuously separate this one Majorana from the other, and then probably we can identify the role played by single Majorana fermion. So in this system, I want to spatially separate the Majorana modes. So that's probably one of the most important requirements in this setup. Okay, so if you just understand my motivation, if you accept my motivation, probably I can directly jump to my result, but probably you are suspicious and might ask, how could I physically separate one Majorana from another spatially. So I can propose a partly realistic system where you can do such a thing. So, in short, I would like to use a topological insulator to separate the Majorana Fermions. So, to explain the idea behind that, let me start from the quantum Hall system. So, quantum Hall system is its idea is quite simple. You have two-dimensional conductor, strong magnetic field, and this is the typical part. The magnetic field should be strong enough, like 10 Tesla or even 20 Tesla. It's not so easy to apply such a strong magnetic field. But anyway, if you apply a strong magnetic field, then this whole conductance is start to quantize. But behind the quantized Hall effect, we have this eddy state. For the existence of eddy state, we could think of some semi-classical picture. Because of the Lorentz force on the strong magnetic field, for example, if the electron goes in this direction, and then because of the Lorentz force, it will deflect it, but at the boundary, it should be reflected. And then it is deflected again, and bounce again, and so on. So effectively, it is confined in this edge of the system, or boundary of the system. And therefore, this is the intuitive explanation of this existence of edge mode. The interesting thing of this edge mode is, of course, it is very robust against any disorder. So let's suppose we have here some impurity, and then because of this semi-classical picture, we can understand that the edge mode cannot have a backscattering, and it just go around and could keep going. So there's no backscattering, and therefore the conductance is perfect. So one conductance unit. So even if you change the size or shape of this conductance, you don't have to calculate. You immediately see that there should exist one edge mode, and this edge mode should be robust. It should go around any impurity it covers. So this is a very important aspect of this quantum Hall effect. Let's think about it slightly different way. So this quantized effect or existence of edge effect is the result of interaction of this charged particle with the external magnetic field. But you can provide this external magnetic field in a different way. If you have a system where the spin-orbit coupling is very strong, then this spin effectively behaves like an external magnetic field. So this effective magnetic field sometimes produces the edge state of this system. So this is the model. So this hypothetical model. Let's suppose you have band structure such that this spin-orbit coupling is described in this simple Hamiltonian. It's a 2x2 Hamiltonian. Sigma, this x component is by the x component of momentum. dy is given by this y component of the momentum, and the z component is given by this momentum square. Then, just to figure out what the simple property of this Hamiltonian, let's think about the uniform system, because this is the simplest example. And then the momentum is a good quantum number, and then you can introduce momentum, and this is the configuration of the spin, or d vector here. So here it would be useful to note that at the zero momentum, the spin is upward, and in the high momentum, the spin over down. So these are boundary conditions. So because of this term, at higher momentum, the spin direction should be always downward and downward. But you can think of two different cases. If the n is positive, in this case you have the spin is upward, and here the spin is downward. And now these the spin at the center and the spin at the high momentum, they are boundary conditions. You cannot change them. But if you introduce now in disorder and you change the shape and so on, these details of the configuration will change. But there's one thing you cannot change in this case. If you start from this boundary condition, at some point you should always have the spin configuration parallel to the sample. But in this case, it's different. You don't have to be. Depending on the details of the system, it starts from the downward speed and slightly decline and go back again. And this behavior will depend on the detail. So these structures are completely different topological structure. And if you have such a structure, then you can have a robust edge state system. That is provided by this, effectively by the spin. This you can think of, again, the semi-classical picture. Let's suppose you have the spin in plane, and now this momentum try to align to the spin. If not, for example, if your particle was bounced from the edge of the sample, and it will try to realign to this spin. So it tries to realign to this system, to this spin. It means that it is deflected. And now if you bounce off from the edge, and then you deflect it again. So you can form this edge state again. So this is somehow equivalent to the quantum Hall Hamiltonian. Indeed, you can mathematically transform this Hamiltonian to the quantum Hall Hamiltonian. So with the exact math. But here we have a problem. So if you have a spin orbit coupling, it preserves the time reversal symmetry. And it cannot be the whole term of the Hamiltonian. You should have the time reversal counterpart of this one. And you have to take into account both. So this is the more real system. In the previous case is just we looked at just a part of it or artificial model, but here this is a more realistic Hamiltonian. Now you have this is the Hamiltonian in a previous slide, and this is the time reversal counterpart. Because the time reversal counterpart corresponds to magnetic field is turned opposite direction, you have two now modes. So instead of one comes from the one block, 2x2 block, and the other is the time reversal counterpart of it. But the spin direction, because of strong spin orbit coupling, the spin direction is locked to the orbital motion. So these edge modes is called helical mode. Again, this edge mode is very robust to the impurity or the shape of the sample, and therefore even without calculating, you can immediately see that it should have 2 units of conductance. And now all these edge states are Dirac fermion. So because we have 2 Dirac fermions, in terms of Majorana, we have 4 Majorana fermions. And now I want to split 3 of them. I want to throw out 3 of them. Or 2 of them, and I want to keep only 2. There are several ways to do that. One way is to put just a normal superconductor here. So just on top of this spin Hall sample, or this epsilon, you just put the usual superconductor we know, the S-wave superconductor. Then, because of the effect of the superconductor, you effectively induce the pairing under the pairing of the electrons underneath this superconductor. So let's think about this pairing of this thing induced by this additional superconductor. Usually in S-wave superconductors, you have pairing between spin up and down and up, so plus momentum and minus momentum. But actually, this is wrong. This is the other way. So you cannot really, because electrons are indistinguishable, you cannot distinguish up-down spin, downward spin. If you have two electrons, you cannot say if this is up or down or up. So you have to make a linear combination of that, because now spin and orbital motion are independent. You have two choices because of the Fermi statistics. Your wave function should be odd under exchange. You can have two choices, either in the spin part or orbital part. But usually energetically, it's energetically favorable to form this odd function in the spin part, and then the orbital part should be even. That means it doesn't depend on the spin and the momentum direction. So it should be a S-wave. That's why usually we have S-wave. But in our case, because of the strong spin-orbit coupling, we can say if it is up-down or down-up, because looking at the attached momentum, because this spin is always attached to, for example, plus momentum, and this spin is always attached to negative spin, negative momentum. Therefore, you can distinguish these electrons by looking at the momentum. That means you cannot, the spin part cannot be independent of the orbital. And there's only one way to make a wave function which is odd under the exchange of two pi. So, for example, you can just look at the momentum part, and then it should be odd under the exchange, meaning that the relative momentum, if the relative momentum is changes, the wave function should change the sign. So it should be P wave. The lowest expansion should be P wave. Then therefore we have this symmetry of the pairing potential. But we have two choices, plus or minus. These are related with each other by time reversal symmetry, and the system breaks because they are degenerate. The system chooses one of them. In other words, we have a spontaneously broken time reversal symmetry. And therefore, going back to this FG mode, because of the spontaneous breaking of this time reversal symmetry, one of them is gone. Which one will be gone, we don't know. You just lower the temperature, one of them is gone. And now it's a P wave, but there is a pairing, and therefore you have a particle Hall symmetry as well. In the presence of particle Hall symmetry, it cannot be of Dirac fermion. It should be Majorana. So from out of these four Majoranas, two of them is gone because of the broken time reversal symmetry, and the other is gone because of the particle Hall symmetry. So just putting this superconductor on top of the quantum spin Hall system, I can have single Majorana fermion at the edge. But this is a discrete change. I can only have either two Majorana or at the same space, or just a single Majorana. I want to continuously separate one of them. Okay, because of the limited time, probably I will not go for details of that, but I would claim that it is indeed possible, and it has been demonstrated experimentally. The remaining step, this is the quantum anomalistic system, and now the remaining thing is that you put additionally superconductor on top of this system. So far, this has been demonstrated. The putting superconductor has not been demonstrated experimentally yet, but I think it is quite close for real experimental realization. So probably we can wait. Okay, so now my system looks like that. Okay, if you are not very interested in, you can just forget about it. You can just think of these two Majorana Fermions, one Dirac fermion, localized Dirac fermion, and you change the level from the external gate voltage. Now here I want to investigate again the impedance or real part of this impedance. Because I'm a theorist, probably I should present you one slide of Hamiltonians. Okay, the Majorana fermions are described by such a Hamiltonian. It's a Majorana fermion propagating only in one direction. And here I have this in real space is a Majorana antiparticle itself, and the momentum space it says this minus. It is related by k and minus k. So this k is epsilon k is the dispersion. It should be linear because it's propagating in one direction. And quantum dot is described the typical one single level Dirac fermion, and it is modulated by external gate voltage or external field. Because of the screening, your field, externally applied field does not apply directly to the system. So it is your field is modified, and this is the internal field, and what this electron really feel is the difference. So this is the finite potential, electric potential difference. And of course, this you know, and this you don't know. And you have to, if you want, you have to calculate this internal field self-consistent. But you can do that. But here, you don't even have to calculate that. And tunneling is described by the coupling between Dirac fermion on the dot and Majorana fermion moving around. So this is my mathematical model. The calculation method is, this is the input here. This electric field is coupled to the charge or number of electrons on the dot. And as a result, you change the current at later time t prime. And this is the input or cause, and this is the output or effect. And this cause and effect is mathematically described by this response function. I think because you are from statistical mechanics group, I think you are familiar with this response function. And response function is the correlator of the input of variable and output variable. In this case, we are output variable is I, and you should put I in principle. But I is nothing but the derivative of charge, and therefore you can calculate the charge correlation, and later you put this omega, and you can take into account the derivative. So basically what I calculate is this thing, and this model is non-interacting. This calculation of this susceptibility or response function should be straightforward. But of course, it's quite tedious. And here is one example. At zero temperature, you can get analytic expression for the impedance using this response function. But I think it's enough to look at just the result. Here I have the plane. This is the value, the universal value, which was predicted before by Mahn-Soo and his collaborators. And this is 1/2. It doesn't depend on the tunneling property, or it doesn't depend on the level position of the quantum dot. But in our case, it strongly depends on, and it never approaches the universal value. It's completely deviated from the universal value. So this now, so if you replace the usual fermionic system by Majorana Fermions, then all this nice universal property of this quantum limit of RC circuit is completely gone, and you have this completely different behavior. One particular feature here is, one interesting thing is that you approaches to 0. If the one Majorana fermion is moved farther and further, and meaning the gamma 2 becomes 0. If, for example, in the limit of you have only one Majorana fermion, the resistance is universally 0 instead of 1/2 of the resistance quantum. So this behavior was surprising, and we checked repeatedly. The part of impedance is responsible for the energy dissipation in this system, and therefore we have to look at the energy dissipation mechanism, or the number, how to create particle-hole pair in this system. So one mechanism is quite useful, the same as before. You take out the electron from here, from the dot, and you fill in. So effectively, you created this particle-hole pair. So here I depicted the Majorana, 2 Majorana modes. If you combine, even though they are spatially separated, if you combine both of them, you can make one fermion or anti-fermion. But in this system, because of the character of the Majorana, which is its own anti-particle, you have another mechanism to create a particle hole. For example, in this case, you take electron here, at the same time, you take electron here. You can do that. And you form a Cooper pair. And this Cooper pair is completely just disappear. Of course, you cost 2 energies here, and therefore it does not conserve the energy, and therefore you have to, and this is the only virtual process, and you break again and fill in this level, and instead of putting back here, you put it here. And then you have effectively, you created particle hole. So now in this case, you have 2 channels to create particle hole pair. Because you have 2 possibilities, you have the coherent sum. You have to sum two of these channels coherently. But if you look at them, here the particle was created first. In this case, hole was created first. And therefore, this particle and hole have been exchanged in these 2 processes. Particles and holes are fermions, and if you exchange, then your amplitude should have a charge of each other, opposite in sign of each other. Therefore, usually they tend to cancel each other. If the one Majorana fermions is far away then these two amplitudes are exactly the same. The magnitude is exactly the same, only the signs are opposite. And therefore they cancel exactly each other, and therefore you cannot have a particle-hole pair, meaning that you don't have energy dissipation in this system. So that's why you have this at zero frequency, and in the single Majorana limit you have zero dissipation or energy relaxation. So we can go to the finite frequency regime. The behavior is even more exotic, and so probably you could focus on this plot, for example. So in this plot, we are taking an extreme limit, and we have only one Majorana fermion. The second Majorana fermion has been completely removed. But you have, as you go to, so we get for different curves means energy levels are close to resonance. Usually you have a resonance, the response should be something like that, right? Lorentz-like behavior, like that. But here, at first it behaves like a resonance, but all of a sudden it drops to zero. Remember that this is the logarithmic scale, therefore this drop is quite drastic. If you plot it in linear scale, it's completely deep peak. So this is quite strange behavior. Of course, this zero has been already explained by the destructive interference, and now we have to understand why it deviates from the resonance behavior. So to understand that, we so the Majorana modes are already expressed in terms of Majorana operators, and now the quantum dot also is expressed in terms of Majorana. This can be always done, right, mathematically. Of course, these two Majoranas occupy the same space, and it does not have direct physical meaning. But at least mathematically, you can always do that. And again, you change D operator into Majorana using two Majorana fermions. And if you look at the tunneling structure, I can give you the cartoon here. It is coupled with each other in this way. One Majorana fermion and one Majorana fermion. These two Majorana fermions are spatially overlapped, but just for your convenience, I split them here in this cartoon. And this Majorana is coupled only to this Majorana, and this Majorana is coupled to this. And these two Majorana fermions, fictitious Majorana fermions, are coupled by this energy level. So this quantum dot energy level behaves like the coupling between two Majorana modes here. And now let's take this extreme, removing these Majorana fermions completely. And then you have only one Majorana traveling modes, and you have one, but it is coupled like that. And now so you can think of many processes. For example, Majorana goes on. This is totally possible, of course. Another possibility is that it goes in and back. There is even another possibility. You go in and go further and go back. And there are three different processes, and you have to combine them all together coherently. And this results in some complicated interference, and probably the simple structure is very close to this Fano resonance. And Fano resonance behavior is depending on the interference strength, you can have resonance behavior or completely anti-resonance behavior, depending on the problem. So in this case, also similar, a little bit more complicated than the usual funnel, and that's why you have this anti-resonance-like behavior. You have, if you only have a single resonance channel, the response to something like that, but now you have anti-resonance behavior. So I think so we now understand why this the energy relaxation mechanism is so complicated in this Majorana case. So we could think of other mechanisms like finite temperature effect and dephasing effect, but I think the time is up. So let me just remind you all that in kind of summary. If you have normal Fermi system, the real part of your impedance should be universal at half. But if you, for example, if you replace it with superconductor, then the behavior would be very similar to this superconducting gap structure. And if you have two Majorana fermions, and then the behavior is, it depends on the coupling of these two Majorana modes, and you can have any value. In the extreme case, you have this strong suppression. And we believe that this is another indication, it could provide another method to probe Majorana fermions in physics. Thank you very much for your attention.
Okay, now it's time for questions. Any students have questions before next? No? Okay.
So usually the universal value of RQ, of the relaxation resistor, is because you fulfill the Corrin-Shiba relation. So here you don't have any Fermi-liquid picture with this Majorana, right? So then you cannot fulfill this rule, or I mean, because Shiba relation automatically ensures that you have this universal behavior of RQ.
We do have Fermi-liquid behavior here.
So then?
But Shiba relation, I haven't investigated, but I will think about it later. But you can observe the Fermi-liquid behavior in this case. For example, here you can see here it's quadratic, and overall also quadratic. So it's a strong indication that it's a Fermi-liquid behavior. And also you have this temperature behavior, also quadratic. So I believe it is a Fermi-liquid behavior. Shiba relation, I don't think it holds here because of interference effect.
But as long as you have a Fermi-liquid system,
But Shiba relation, I think you can apply only when these modes are independent. Don't you? I have to think about it. So to be honest, I haven't thought about it.
Yes, the Majorana Fermions you are considering here along the edge, they are really traveling along the edge.
Yes.
So in this sense, they are completely different from localized Majoranas in nanowires.
Indeed,
No?
indeed.
So this is an essential ingredient for you that they may be traveling along the edge.
Right. So dispersion here, the dispersion relation also important. Not only the Majorana. If you, you're right. So usually how do you confirm the Majorana? And usually they say Majorana. It is Majorana because it's zero energy. But I think it is wrong, because you can have zero state even though you have. If you don't have a particle Hall symmetry, you can have state at zero energy. So this is another example. You can have finite energy, but still it's a Majorana. So if you take dagger It's the same. So it's quite different from the localized Majorana mode. So it's an important thing is that you have to have a continuum dispersion. Otherwise, you cannot create a continuum of particle-hole pair. And then, without particle-hole pair, you cannot dissipate energy. So I think it's important to have a traveling mode.
But then in this picture, this image that anti-state, or let's say the conjugate state, is the one at opposite energy is no longer true.
This is true. This is related to this. Like that here. Okay.
Yeah, there's something.
But in this case, the anti-state has the same energy.
No, it has. So you have, if you take here, it brings to minus k, so its energy becomes negative. But the important thing is that in the real space, it's Majorana, and of course this means that this similar to this. If you take the Fourier transform of this, that means you have this relation, right? So that's the same. So Majorana character is hidden here, but it doesn't need to be zero energy. The Dirac equation, you have finite energy, right? Even mass. So massive Dirac equation can have real.
Actually, you have a reservoir with around 50, right?
Which one?
I mean, it's like a reservoir.
Yes, it's like a reservoir. Yeah, but special kind of reservoir. Yes.
Okay, so the other question there is, okay, you consider just a single level quantum dot, and we know that charging effects are very important in these dots. So do you plan to extend these to consider cycle of interaction?
No.
It's already difficult.
Because this is already complicated. But well, yeah, Rosa is interested in some different aspect of exactly the same model. Okay, I try to keep the model as simple as possible before going to make it complicated. Yes.
In the quantum dot, you separate the one electron level into two microns.
Yes, right.
Are they separated in energy?
No. They have the same energy. They have the sense. They occupy the same space. It's this Majorana representation is just mathematical, artificial.
Okay, so thank you for your talk.
As time goes.